Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply the work-energy theorem. So what we're going to do is we're going to take a look at this biker here, which is going to start at this position at a speed of approximately 0. So she's going very slow here. I'll put approximately 0 at that point. And what we're going to do is calculate the speed of this biker at the bottom of this hill here. Under the following assumptions. First assumption is that any frictional forces acting on the bike or air drag or anything like that are very small, so I put approximately 0. And 2, no pedaling. This person's not going to be pumping the pedals trying to accelerate the bike, and that's a very important assumption for this problem, because if this person were working these pedals hard, that would be a work input in a system that has to be taken into account. So in this example, we'll just assume that away, because this example is just meant to demonstrate how to apply these principles. So before we even begin, the old saying, a picture's worth 1,000 words, or I like to say in physics it's worth 2,000 words. So I'm going to work a little bit more on my picture. Specifically, I'm going to try to describe graphically that this person is speeding up, that their speed is going to be increasing as they go down the hill, and we do that with what are called motion diagrams. Remember the little snapshots in time here? And again, what I'm doing here is I'm just drawing a dot to represent the person, the system, because I don't want to redraw the biker the entire time over and over and over. Right? And you notice that the dots are getting further apart, and that's because, again, as the person moves faster and faster and faster, she'd be covering more and more and more distance. All right, now I might even throw some velocity vectors in. So here the velocity vector is very small, but as she accelerates down the hill, her speed would increase, so that vector would get larger and larger and larger. And there's her final velocity vector. I'm going to go ahead and call that V2 here, and I'm going to call this position 1 and this position 2. And the reason is because when you write out the theorem of work and energy, it's a theorem relating states or positions. So this is what I'm going to call position 1, this is what I'm calling position 2, and now I'm going to write out the work-energy theorem, which says PE1 plus KE1 plus work from 1 to 2. I don't always write the 1 to 2, but it's any work on the system between state 1 and state 2, is equal to PE2 plus KE2. Right. Now, the work-energy theorem. What we do now is we have to think about these potential energies. So remember, gravitational potential energy, if you've seen my video on that, is equal to mgh, as long as we're at the surface of the Earth and not relatively high, where the g is 9.8 meter per second squared, or 9.8 newton per kilogram, depending on what units you like. Right? The h, we have to decide where to measure the h from. That's called our datum. And remember, you get to choose that. The lowest point in the diagram is usually a good place to put a datum, so I'm going to go ahead and call this my datum. I guess before I do, I'm going to move that equation, because I put it kind of right in my way here. This little computer is very good for stuff like that. All right, so I'm going to go ahead and put my datum in blue here. So there's my datum. Now, really, in reality, the datum should go through what's called the center of mass here. I think this is good enough for this problem. I'm going to say that the person has 0 potential energy when they're in this position. They've got a potential energy of mgh, where the h is 10 meters when they're in this position. That'll be good enough. So I'll go ahead and leave that alone. There's my datum. So PE1 is equal to mgh, where this is my h. Now, if you have a problem that has multiple heights, you might put it like an h1 and an h2 for the second height. But this problem really only has one height here to worry about, so I'm going to go ahead and just leave it mgh. This term is positive because the person is above the datum. Okay. Right. In this example, KE1 is basically 0 or approximately 0 because we assumed that the velocity was 0. And remember that kinetic energy is 1/2 mv squared. So if your v is approximately 0, then your kinetic energy is approximately 0. Work term. Now the work term is going to be a 0. I'm going to come back and talk about why that is here after I get the equation written out. All right, PE2. So person 2 here now is at our lowest point. Basically, they're at the datum, so we would say they have a height of 0. So I'm going to call that potential energy 0. And then KE2 is equal to 1/2 mv squared. Now, there's only one velocity in the problem. That velocity is the velocity at position 2, v2. So whether you put a subscript on here or not, I'm going to go ahead and just leave it off for this video, because this video is intended for to be not a complex problem. But when you have multiple velocities in a problem, that's where you need the subscripts. But in these two pictures, there's no velocity here, there's a velocity here, so this v is the velocity at position 2. That's the one I labeled v2 in the picture. All right, let me go back to that work term. So in the work-energy theorem, the work term is generally for non-conservative forces, right? And a non-conservative force is a force that changes the net energy of the system. If we think about the forces acting on this person as they accelerate down the hill, we got the gravitational force, which is down. And, you know, I was asked the question, did that force do work? Well, in this example, the answer is yes, because force, and there's a vertical displacement. However, that term is taken into account with this potential energy. If we try to take it into account again, we'll be double dipping on it. Right? There's normal forces that act perpendicular to the ground, maybe here and here. And what you have to realize is that, you know, as this cycle moves along this path, the normal force is changing direction, and it's always perpendicular to the path. So because the normal force is always perpendicular, it's not doing any work. Right? We assumed friction and air drag are small, no other forces to worry about. So that's why the work term is 0. If we tried to include a frictional force or air drag, that's where this would go. So we've got our work-energy theorem equation written out. Now let's rewrite it. You'll notice that we don't need the zeros, and the mass divides out, right, because it's in each term. So we're going to have g times h equals v squared over 2. And at this point, I'm just going to go ahead and put numbers in. So g is the gravitational acceleration, or gravitational field strength, however you prefer to think about it, 9.8 meter per second squared. The height is the 10 meters, equals v squared over 2. Next step here would be to multiply both sides by 2. So if we do, what we get is 196 on this side. Units, now meter times meter is meter squared over second squared. That might look a little funny, but it's fine because what we have on the right hand side is v squared. So we would solve this by square rooting both sides. And I get about 14 meter per second out of that. I'll just put that over here. So our v, which is v2, is approximately 14 meter per second when this biker gets to the bottom of the hill. So again, this video was just intended to be a nice simple example of the work-energy theorem. Hope it demonstrates, you know, how to apply the theorem and figure out what each term is and use it to, in this case, find the speed of this biker. Have a great day.